Mr. Tyson here with video 6.4, the final video in Unit 6, which may seem a little strange because we're going to jump off and talk about something that doesn't seem to have to do with circles, which is what we've been talking about, and that is the law of universal gravitation. Of course, the law of universal gravitation, which was put forward by Isaac Newton, really does kind of have to do with circles, because one of the things that they were wondering about was how exactly is it that planets can orbit one another, and they assumed that the orbits were circular paths. So they were wondering, oh, okay, how does that happen? How does a planet circle around another planet? And that, of course, led Newton to the idea that, well, it must be gravity. Like there's no magic string connecting the moon to Earth, and yet the moon revolves around the Earth in a consistently circular path. So what is it that's pulling on the moon? Because we know in order for the moon to move in a circle, it has to have a centripetal force acting on it. And so there's no gigantic string, so it's got to be some other force, and that force, of course, is the force of gravity. The force of gravity between the moon and the Earth is what provides the centripetal force that allows the moon to move in a circle around the Earth. Newton was trying to picture how that happens. He imagined, if you shoot an object at a certain speed, like, if you shoot it not too fast, it's going to fall. It follows a path, kind of circular path as it falls. You shoot a little faster, the circle gets a little bigger. Shoot a little faster, the circle gets a little bigger. If you could shoot it fast enough, you would be able to shoot it in a circular orbit, because by the time it had fallen, it would have fallen only enough so that it fell in the circular path of the Earth that it was orbiting around. So, like, you think about the moon, it's heading to the right. Let's say it's orbiting this way, and so it wants to go on a circular path, right? It wants to go that way, but it doesn't, because it's got a centripetal force acting on it. So that centripetal force is pulling it to the Earth. Why doesn't it crash into the Earth? Well, it's moving this way at such a speed so that by the time it's fallen, so let's say it moves this over to here. By the time it's fallen this much, it's still the same distance away from the Earth, because the path that it's falling along, because of how fast it's moving, exactly creates the path of the circle that goes around the Earth. All right, so let's talk now about the idea of gravitational force. Gravitational force is a force that attracts every particle of matter in the universe to every other particle of matter in the universe. And that's where kind of Newton started, that all of matter is pulling towards itself. But it depends how fast, the amount of the force depends on two things. It depends on how far apart the objects are, and it depends on how large the objects are. So, for instance, the Earth, gigantic object, right? It's got a lot of mass. Therefore, it's capable of pulling with a lot of gravitational force. The moon, also pretty large, not as large as the Earth, capable of pulling with gravitational force. But the fact is that we know from Newton's third law that whatever force is between them is a mutual force, equal in opposite directions. So however hard the Earth is pulling at the moon, that's how hard the moon is pulling at the Earth. It's the same forces. But the force is affected by two things. It's affected by the size of the object and the distance between them. So the larger the object, the more gravitational force there will be, and the further apart the objects are, the less gravitational force there will be. Okay, so that means that it's directly proportional to mass. It is inversely proportional to the square of the distance between the objects, and that is expressed in the formula that Newton created. The force of gravity that exists between any two objects is equal to g, which is the number 6.673 times 10 to the negative 11th. It's just some number that has to be in the formula. It's called a constant. It's called the gravitational constant. You do not have to memorize it. So it just has to be there in the formula to make the formula work. But the mass of the first object times the mass of the second object divided by the distance between them squared. So r stands for the distance between the masses. We call it a radius. Think about it as a radius of the circle, like the moon going around the Earth. Think about the distance between the moon and the Earth. That actually is the radius of the giant circle that the moon is making as it goes around the Earth. But this formula allows you to calculate how many newtons of force there are because of the gravity. So gravity exists between any two objects. I mean, it exists between, like, if you put two pencils down on a table, right? There is gravity attraction between those two pencils. My ability to draw pencils is rather limited. But if you put two pencils down, they're pulling towards each other. They might say, oh, that's silly. They don't roll towards each other. Well, no, they don't, because gravity force is actually a very weak force. So the amount of force between those two pencils is so incredibly small that it isn't sufficient to make them move towards each other against the friction of the table that they're sitting on. Now, put those same pencils in outer space. Just put them near each other in outer space, and after a while, they will drift towards each other and touch. Okay, so the gravity force is real. It exists. When you're calculating gravity force and you calculate R, so for instance, what if you want to know the force between you and the Earth? Now, you're on the Earth, right? So the distance between you and the Earth, you might think, is 0 because I'm on the Earth. But the Earth is a gigantic circle. When you calculate the distance between you and the Earth, you're actually calculating the distance between you and the center of the Earth, so that this becomes R. So if you ever have an object that's on Earth and you want to calculate the gravity between the object and the Earth, you have to use the radius of the Earth as your R value. Same thing if it were the Moon. Whatever the radius of the Moon is, or any other object. You know, if a person's on the Moon, then you want to calculate gravity, you have to use the R of the Moon and consider that to be the distance between the two objects. So an example, find the gravity force that Earth exerts on the Moon. All right, look at these gigantic masses for the Earth and the Moon. And the distance between them, also a gigantic number. So when you do these problems, a lot of times you have to use scientific notation on your calculator. But it's just a formula, like any other formula. So the force of gravity between them is equal to G times the mass of the first object times the mass of the second object divided by the radius squared. All right, so what do we know? Sorry, I did these by hand, so they're a little sloppy. But we got the G is this number here. That's always going to be in the formula. And then the mass of the Earth is given here in kilograms times the mass of the Moon, which was given in kilograms, divided by the distance between them squared. All right, and that would be the distance between their centers. So whatever objects you're using, you're really measuring the distance between their centers. And that gives you your answer. One more example, find the distance between a 0.3 kilogram billiard ball and a 0.4 kilogram billiard ball or pool ball if the magnitude of the gravitational force between them is 8.92 times 10 to the negative 11th newtons. Look at how small that force is, ridiculously tiny amount of force, just like the pencils I was referring to. Here's the same formula, they're just asking you to find something different, a different one of the letters. So here they've told us that the force of gravity is 8.92 times 10 to the negative 11th, so that goes in the spot for the force of gravity in the formula. G is always going to be there, as I said. We have the mass of the first ball, the mass of the second ball, and what we're trying to find is R squared. So this is just a little bit of algebraic manipulation. Personally, I like to solve problems like this as proportions. I put a 1 underneath this number, and I cross multiply. 1 times 8 times 10 to the negative 12th is 8 times 10 to the negative 12th. And then this multiplied by R squared, and then I went through and solved for R squared. Finally, I finished up by square rooting both sides and getting my radius as about 0.3 meters. All right, and that is the end of the lesson on gravitational attraction. I hope you found it attracting.